Okay, good morning, everyone. I said I was not going to be here, and I'm here, but only for like maybe the first 15 minutes before I have to run to a personal appointment. So I wanted to start off today with a really brief top hat question, just to kind of check your understanding on complex variables, and then things that we're going to be, contents we covered on homework 1, which is, as a reminder, due on Wednesday. If you went to Carmen, you would see that the answers, just the answers, none of the work in between is posted already. It was posted sometime late last night. So I sent an email also last night with the join code for Top Hat. In case you have not seen your email yet, the join code is probably not legible at all. Let me zoom in. 533972. So for those, yes? I don't know. Is anyone else having success or the same issue? What? Okay. Some people are getting it, some are having it. Okay. I don't know. So I had another student who asked about access to Top Hat. So this is not for grade, this is just for fun, so you're not going to get points by that access. But there is, if you search Ohio State Top Hat, there is someone at our university in charge of figuring out all these digital issues. So I really recommend contacting them. Yes.
I think there's also an option to just do it through like your like text message as well.
Okay.
Sure how to
Through text messaging?
yeah, in case you want to.
All right, I'll have to follow up on that. Okay. So 533972. Do you want to join in? All right, so today's problem. Okay, so how do I zoom out? Okay. So here you can see on the board. So today's problem is it gives you a transfer function, or we won't call it transfer function today, I guess. We'll just call it a function of complex variables. And you see the form right here. S plus c squared over s plus a, s minus bi, s plus di. And then it gives you a graphical representation of where s is, where d is, where a is, where c is, and then b, in terms of, I guess, those dimensions. And then it gives you some angles and some distances of vectors, or magnitudes of some vectors. And so the question is, with s, as specified in this plot, what is f of s in terms of its magnitude and phase angle of f of s? So by that, I mean if we were to rewrite f of s into a complex number with a magnitude and phase, what would the magnitude and phase be? So we'll take about 4 or 5 minutes to kind of think through this, and then we'll see what the answers were from the class, and we'll go through, and hopefully, if there's any confusion, we'll try and clear that up. So I guess I just noticed that there is a text option at the top too. You can see it. So those who are unable to access Top Hat right now can do that. Okay, so it looks like most everyone has responded, and I guess we have 13 seconds left on this. So we'll go through the answers here. Time is running out. Okay, so the vast majority of you got it right. So the answer is B. So I guess my question from here on then is, why is it B? And so we'll walk through why is it B, just in case there's any confusion here. But so I guess first off, can someone please explain to me why is it B and not A, C, or D? What is your rationale for finding B? Yes.
We know that the numerator is going to be having like a positive like angle, so it's plus you have that square, so you know it's going to be 2, 5, 3 minus 5, 1 minus 5, 4.
Okay. So that eliminates it to B or C. So as a sorry, what's your name? What's your name? Tyler. So as Tyler was saying, what you have here in terms of the form of this function here. So I'm just adding an extra sheet here. This is Top Hat question. Okay, so the form of this function was f of s is equal to s plus a squared. That's not right. S plus, what was it, c? C, right? The top? S plus a, s minus bi, s plus di. So the first thing that was recognized is that you have a s plus c squared in the numerator. Okay, so if we look at how we could rewrite this and say just look at the numerator, we could have rewritten this as s minus negative c squared in the numerator, and this we could equivalently write this individual term here we can rewrite as some sort of r e to the I theta. And we'll get to what that form looks like in a second. Denominator, I'm not changing anything. But looking at what was asked in the question here, s plus c squared, c is given. All right, so c, if it's s plus c squared, that means that we can rewrite this s minus negative c. Negative c is at this location in the complex plane, right? Assuming, I didn't specify, but assuming c is a real number, that would be in this location. And we see that the distance between negative c and s has a distance of r3 and a phase angle of theta 3. All right, so then what differentiates the solution here in terms of between b and a is the fact that the numerator has a squared term in it. Right? So if I look at this, I could say this is equal to some sort of complex number, or I could say this is equal to this vector going from negative c to s squared. Right? So if I look at r3 ei p3, say I have this squared, right, this ends up being r3 squared e I to the 2 v3 in the numerator. Any questions about that discrepancy between answer B and answer A? Good there? Okay, so then the other answers to this, the other answers, I guess the other components of these fall out if you follow the same exact kind of procedure here. The difficult part is you have a square in the numerator where the other ones do not have a squared. So A is eliminated because it has to be 2 phi3 and R3 squared. Denominator follows, so B is correct everywhere in terms of R1 is the distance between negative A and S. So that matches up. R2 is the distance between, that'd be negative or positive B and S. And then R4 is the distance between negative DI and S. Okay, so then these all follow. When you're looking at addition subtraction here, so you're looking at phase, we're actually looking at addition and subtraction. And that comes from the fact that if we were to fill in the rest of this denominator, which I left out thus far, is that we are concerning ourselves with the denominator here. Let's fill this in. This would be R1 E I theta 1, or phi 1, R2 E I theta 2, and R4, and I believe R4, if I go back to the answer, sorry, it's R2 does not have a phase angle, so I'll get back to that. So R2 doesn't have a phase angle because this vector is going due east. Okay, so R2, or phi2 is equal to 0. R4, EI, phi4. Okay, so I combine these all together. In the denominator, we're going to get R1, R2, R4, EI, phi1 plus phi4. But it's in the denominator, right? So when I combine these all together, in terms of how exponents work, it's going to be the exponent in the numerator minus the exponent in the denominator. So this is going to give me a final answer. R3 squared over R1, R2, R4, EI 2 phi 3 minus phi 1 minus phi 4. Okay, give me some magnitude and phase. Okay. Any questions about this kind of more conceptual problem? So last thing I want to touch on before I head out. Okay, so we finished Friday's class talking about this map. And so we got partially through this map, and I want to finish this off before I left. So far we looked at the influence of poles to Laplace transforms that are on the real axis, right? And so we're going to make this a little more complicated. We're looking at as poles get off the real axis, what does this do in terms of responses? So the main thing, just to recap from Friday's lecture, is that poles on the real axis are defined by exponential solutions. So if I have a Laplace transform, that's in the frequency domain, I convert that Laplace transform into the time domain. It's going to be a time domain solution that is in the form of exponentials. By that we mean forms of, say, e to the minus at, right? That's going to be the form of the solution. All right, so then the other thing to recognize is that if I'm in the left half plane, these are converging exponentials. If I go farther into the left half plane, it converges faster. And then if I flip over to the right half plane, now we have diverging exponentials, or exponentials that go off to infinity as time increases. Okay. So that's the main thing to take away from Friday's lecture. Now we're going to start to talk about what happens on the imaginary axis. So say, for instance, I have a Laplace transform, and I have poles of this Laplace transform of here and here. So just to note, real poles, we can have just one of these. We have 3 of them, we have 4 of them, doesn't matter. You can have any number of real poles that you want. In terms of if a pole has an imaginary component, it always has a brother or sister, right? Right? Or a complex conjugate. Right? So if we have a pole at some sort of positive omega I, we're always going to have a pole at negative omega I. That always happens. That's just the way solutions to polynomials work. Okay. So what does the time domain solution look like if I have a pair of poles on the imaginary axis? What does this look like in time? Yes. Oscillates indefinitely. Yep. Okay. So this poles on the imaginary axis correspond to solutions that are composed of cosines and sines. So that means it's going to, if cosine and sine, that is a function that oscillates indefinitely. And so we have a solution that looks like this. It's my best approximation of a cosine and sine. Okay. All right. So now, before we said that the real axis determines how fast the solution converges. The imaginary axis actually determines how fast it oscillates. So if I have another set of poles, and I want to, for a point of comparison, these new set of poles on the imaginary axis are closer to the real axis, it's going to oscillate more slowly, or have a lower frequency. In comparison. Okay. Now the last thing before I jet is that what happens is we have complex conjugate poles. So meaning that they have a real part and an imaginary part. Sorry, complex conjugate poles are complex, I mean. So they have a real part and an imaginary part. And let's say we're going to start off the discussion that they are in the left half plane. What does this look like in terms of time domain solutions? Someone from the back. What does this look like in terms of a time domain solution for poles of this nature? Yes?
It oscillates but converges at 0.
Converges to 0, right? Yeah, converges to 0. Exactly. So it's a mixture of these two, right? So if we look at the real poles in the left half plane, these converge, right, in time to 0, but it also is going to have an oscillatory function to it, right? So it's going to be bounded by some sort of envelope, which determines how it converges, but it's going to oscillate in between. So it eventually converges to 0. Okay, if I were to shift or shoot off into the right half plane for my pole locations, say for instance, I had pole locations here and here. All right, so my envelope, the exponential is still going to define the envelope, but now it's going to oscillate in a manner that goes off to infinity. Okay. So, of all the content that you learned in 3260, these relationships in terms of the correspondence between poles and time domain solutions is the most important for you to know. Okay? So if you're uncomfortable with this map and don't quite understand this yet, you need to review this because we're looking at maps like this throughout this semester. Okay. One thing I want to say before I made that comment to explain the importance, I wanted to show exactly what these axes mean. So just to add to your notes, this direction in terms of a pole, if we increase the imaginary component of a pole, this means increasing frequency. If I move a pole to the left, so say for instance I have a pole that's -2 and I move it to -4, and in controlled systems we're going to be able to do this. We're actually going to move poles around the complex plane. This is going to be increasing decay rate. And then if I were to move a pole farther to the right, this would be increasing explosion rate. Okay. And so when I left off on Friday, I said, okay, we're going to be designing systems such that they behave in a favorable manner. And we kind of went through the idea of, okay, what would be favorable in this complex plane? And so first off, bare minimum is we're devising systems such that we ensure that all the poles are in the left half plane because we want to have systems that converge. So imagine this is your cruise control over here, and you did a really terrible job, and this is how your cruise control speed converges to 65 miles per hour, you're going to kill someone, right? Someone's going to be in a lot of trouble because their car is going to be oscillating and getting larger oscillations around 65 miles per hour. What we want is something that converges nicely to say 65 miles per hour, right? So when we design things, we're going to make sure that the poles are in the right location. We're designing systems. Okay. All right, with that, I have to run. Instructor Lake is going to take over for me, and then I'll see you all on Tuesday if you're going to office hours, and if not, on Wednesday. Just leave this with you.
Oh, sure, yeah, I'll take care of it. All right, good morning. You guys are stuck with me now for a little bit. So I'm going to spend the rest of the time for this class reviewing transfer functions, and then depending how much time I have, I'm also reviewing Bode plots for you all. Okay, so, and this is my first time using one of these things, so we'll see how good my handwriting is. All right, so to get started, can someone remind me, what is the definition of a transfer function? Anybody? In what domain? Time or frequency? Yeah, I heard it. Frequency. Yep. So it's a ratio of the Laplace transform of the output to the input. So let me write this down for you guys. Okay, here you are. Okay. Woo, it's going to be interesting. Sorry, forgive my handwriting. So it's a transfer function is the ratio of the Laplace transform of the output to the input of some system given, specifically, what are the initial conditions for a transfer function? 0, yeah, given the initial, I'm going to abbreviate this, ICs are equal to 0. Okay. Sorry, that looks really terrible handwriting. I'm getting better. Okay, and then to make a remark, we're going to say notice transfer functions abbreviate that, purely depend on the system parameters. They're not influenced by a non-homogeneous forcing function or, like we said, initial conditions. So let me write that out. So I'm going to write that they are not influenced by non-homogeneous forcing functions. So or initial conditions. All right, so should be Okay, so then let's formally define them, or let's do some, or write out some math to help with this definition. There you go. So we're going to say let G of S, our transfer function, equal numerator n of S over the denominator of S. There's two functions defined in the frequency domain. So let this be a transfer function. And then we'll define that D of S is the characteristic equation and that the lowest power of S in the polynomial, let me actually, I'll just say in the polynomial D of S is termed the system type. So as an example, transfer function, let's say G of S is equal to beta sub 3 S cubed plus beta sub 2 S squared plus beta sub 1 S plus beta sub naught divided by S squared times alpha sub 3 S cubed plus alpha sub 2 S squared plus alpha sub 1 S plus alpha naught. So given that transfer function, what's the system type for this transfer function? Go up. It's higher. Yeah, S squared is a 2. It's a type 2 system. So another way to say this second point to define a system type is also the number of poles at the origin. So if we look at this transfer function, we have an S squared term by itself. So that means there's 2 poles at the origin, and this is a type 2 system. All right, and then there's a note on the filled-in version of your notes. In a few weeks, Dr. Helley says you'll use these definitions to look at some properties specific to type 0, 1, and 2 systems. All right, so then point number 3, we're going to define something called how proper a transfer function is. So if the order of D of S is greater than the order of our polynomial n of S, we'll say the transfer function, I'm going to abbreviate that TF, is what we call strictly proper. I'm going to run out of room. Okay, so that's one definition, and that's what we'll be mostly using in this class this semester. The other cases are, let's put a bullet point here. So if the order of D of S greater than or equal to the order of n of s, our numerator polynomial. We call that proper. I connected my dots. And let's make a small note over here. If the order of n of s is, if instead the order of n of s is greater than or equal to the order of d of s, we'll call that improper. Let me draw an arrow. So those are just definitions. But for this class, let me change my pen color. We'll be working with this one, the strictly proper. All right, are there any questions about the definition of a transfer function? Yeah?
The strictly proper and just proper, is there a difference? Is it just equal sign?
Let's see, strictly proper versus proper, if there's a difference. Yeah, just the equal sign. All right. On to an example. So now we're going to look at an example with, drawing random lines everywhere. Look at an example with two pulleys connected by a flexible band that acts like a torsional spring. Oh, yeah.
Question on the definition.
Oh, sure.
If it's equal to each other, the orders, which is it, proper or improper?
Oh, good point. It might be a typo. Let's see. Oh, yep, that's a typo. So improper should just be greater than. And then with the equal to should be proper. Thank you for pointing that out. Okay. Okay, so then let's move on to an example where we have these two pulleys drawn here, connected by a rubber band that we model as a torsional spring. And what we're going to do is define the transfer functions for these relating both the output displacement of the first inertia with the input torque and the output displacement on the second inertia with the input torque. That's also, the input torque is only on the first inertia. So then if we were, get the hang of this. Okay, so then what we're going to do is we would normally, like in 3260, we'd start off with a free body diagram and write the equations of motion from that. Here I'm just going to jump straight to writing the equations of motion. So for the first inertia, we get J1 times theta 1 double dot of t plus, oh, actually, let me do this different. That's equal to the input torque, function of time, plus k times theta 2, the function of time, minus theta 1 of t. And then for the second inertia, we have J2, theta 2, double dot. Sorry, I merged my dots. J2 double dot. Come on. Try this again. Oh boy. Okay, I might actually be to the projector if this thing keeps up. Okay. There we go. Okay, sorry about that. Okay, J2 theta 2 double dot of t is equal to negative k times theta 2 of t minus theta 1 of t. All right, so if I ultimately want to write a transfer function, what do I need to do to these differential equations? Yeah, Laplace transform. So we're going to take a Laplace transform of both of these. So let's draw an L onto the side of each one. Okay, so if I do that, I get J1 S squared theta 1. That's a capital theta, or my attempt at drawing a capital theta. It's equal to T of S plus K times theta 2 minus theta 1 of S. So that's for the first equation. So then for the second one, we'll do J2 S squared theta 2 of S is equal to negative K times theta 2 minus theta 1. So we have two equations in the frequency domain. They're both in terms of theta 1, theta 2. We have one that has a t in it. So what we want to do is manipulate these so we can isolate each of the output displacement variables with the force. So to start that, we're going to rearrange the second equation here. And we can find that theta 2 of S is equal to K over J2 S squared plus K times theta 1 of S. So we've just rewritten theta 2 in terms of theta 1. And then we're going to substitute that back into the first differential equation, the Laplace, or the frequency domain that we haven't used yet. If we do that, we get J1 S squared theta 1 of S equal to T of S plus K times K over J2 S squared plus K times theta 1 minus theta 1. All right, and then the next part of this is just doing some simplification with some math. So we're going to expand or do some simplifications, and if we do that, we get J1 S squared. Not sure what to go on. Okay, sorry about that. Things got a mind of its own sometimes. Okay, J1. We get J1 S squared theta 1 times J2 S squared plus K is equal to T of S times J2 S squared plus K plus K. Actually, I'm going to go on the next line because I'm not giving myself enough room. Plus K times K theta 1 minus theta 1 times J2 S squared plus K. So we basically just got this term out of the denominator, this J2S squared plus K. All right, and then do some more rearranging. We can get down to, let me draw a line to separate these out. So do some last math manipulations. We get down to an equation J1, J2 S squared, theta 1, plus J1 times KS squared times theta 1 is is equal to J2 S squared plus K times T of S. And a simplification happens that two terms end up canceling, so then we just get left with K times J2 S squared times theta 1 of S. So this is just doing some algebra to get down to some simpler forms of our equations. And then from here, you can find the transfer function, theta 1 over T is equal to J2 S squared plus K divided by S squared times J1 J2 S squared plus K times J1 plus J2 so that's that's one of our relationships. So we already found an expression of theta 2 in terms of theta 1. So then if we were to plug this back in, we could then also find a relationship for theta 2. So theta 2 of S over T of S is going to be just K divided by S squared times J1 J2 S squared, same denominator as the other transfer function actually, K times J1 plus J2, and these are the two transfer functions that define our system. Are there any? Oh, yeah.
Could we ever have our input torque be on the like in the denominator of the transfer function, but also be on the right hand side of the equation too, like at the same time?
Okay, so the question is, can the input torque be on the left hand side and on the right hand side? To really be a transfer function, you need a ratio of the output of the input. So I don't believe that's a case you would ever, it would come up. And usually you can't, if you're going to have something where you can't fully isolate a variable, that's probably going to happen in a nonlinear system. You're only going to develop a transfer function for a linear system. Yeah? Yeah, you could do, the question is, could we use Cramer's rule? That's another math tool. This is one way to solve the problem. There's multiple ways to get down to the transfer functions. All right. Any other questions? Okay. So then there's just some summary material here. My button. Just kind of summarizing the transfer function. That it's a concise relationship between the input and output. And then basically given your input torque, you could relate these to your output displacements for each of the inertias. Then a note about how theta 1 and theta 2, if we look up at their transfer functions, theta 1 is not explicitly written out as a function of theta 2 and vice versa, but they have the same dynamics, or they have similar dynamics in that they both have the same pole locations. All right, so then let's move on to frequency response. So I'm going to start off with a proposition that if all the poles of our transfer function g of s are in the left half plane, and if, call this our system output, y of t is equal to the Laplace, the inverse Laplace transform of g of s times a omega over s squared plus omega squared. That's just a Laplace. Let me write that a little better. Where this a omega over s squared plus omega squared, that's just a Laplace transform of a sine function. Say as t becomes large, the steady state or, aka particular solution is given by y sub ss, I'm going to write this out as y ss of t, is equal to a times the magnitude of g. Dr. Helsley likes to use I, so I like j's for imaginary numbers, but I'll stick with his convention. So a of g of j omega, g of I omega, sine of omega t, plus the phase angle of g of I omega. Switch colors. So A is the input magnitude. This magnitude of g of j omega, that's the system gain. This phase angle of g of I omega is the system phase. Actually, I'm going to erase these. So these are just to help you label these in your notes. I ran out of room, so I'm going to actually erase these so I can write out the definition. Okay, so then we're going to define our magnitude, g of I omega, equal to square root of the real part of our transfer function, g of I omega squared, plus the imaginary component of g of I omega squared. And then our phase angle, g of I omega, be the tangent inverse, so to the negative 1 of the imaginary of, I'm just going to write this as g, imaginary of g of I omega over the real part of g of I omega. So this gives us a quick way that given an input, a harmonic input, if we know the input frequency, we know the input amplitude A. These magnitude and phase angles are things that we can pull from a Bode plot, which I know everyone, or like I'm pretty sure every section of 3260's definitely done those because of how important they are. So we're talking about how important the frequency response is. The main idea is that given an input to your system that is harmonic, it's really tiny, zoom in, there you go. All right, so given a harmonic input to your system, we'll call it U of t here, so say it's cosine of omega t, we can calculate the time domain form of the solution. In this case, it's to scale, or for any linear system, the output given a harmonic input will be the input amplitude of the system, A, scaled by some magnitude of g of I omega, and phase shifted. So if we look at these two plots, this is our input cosine, goes up to A, but then we've scaled the sinusoid and the amplitude, and also there's a slight phase shift. So this is true for any linear system. Let me scroll back out. And I'll wrap up with one last definition. So this is for any harmonic input. This can be also, we can also break down non-harmonic inputs in terms of harmonic functions for an approximation. Can anyone tell me what the name of that equation is that we could rewrite non-harmonic functions as a harmonic function? Someone said it really quietly. Fourier, yeah, Fourier. The Fourier series approximation. So then, to just generalize things so a Fourier series approximation breaks something down into a summation of sinusoids, or of harmonic functions. So just to generalize the equations that we just wrote. Sorry, this thing goes. Okay, we're going to just generalize this so that if we have an input that is a summation of, I'll just write it as cosine function. So A sub k for cosine of omega k plus phi of k. Our input is instead not just one harmonic, but a summation of harmonics. We could write our output function, y of t, is a summation of k equals 1 to n, a sub k, g of I omega k, cosine of omega k, t, sorry, this thing has a mind of its own. Okay, omega k times t plus phase phi k plus our phase from our dynamics, g of I omega k. All right, so I'm out of time. Next time you'll finish up with just going through an example on Bode plots. Dr. Helsley will be back. If you guys have any questions you want to talk to me about, I'll be here. So have a good day.